Okay, hello everybody. Let's start. Today, we plan to talk about a special kind of neural network, basically convolutional neural networks, which are, as you know, a very popular type of neural architecture. And the key reason that I would like to discuss this convolutional neural network is that first you get an idea of what it means to have different types of neural architecture, some interesting concepts behind these popular neural architectures. Also, more importantly, the key reason actually is that when it comes to understand some of these concepts at the system level as well as the hardware level, we will use the concepts here to make things more concrete. Basically, convolutional neural networks are the ones who have been deployed a lot in practice, and that's why they are the most popular type of neural architectures, and why it matters for us to understand the connection to the system and the hardware, because there are lots of opportunities for optimization, for example, for the memory aspect of these neural architectures, the kind of concepts behind how we could compress these kind of architectures and deploy them into this kind of basically a small hardware platforms, right, with different macro architectures. So we need to make things more concrete when it comes to discussing about these optimization aspects as well as the hardware aspects, and some of the details that we discuss across system stack. We should have a good understanding of these important concepts behind ConvNets. Okay, so before we go into the detail, do you have any question?
Oh, I saw these slides on the lecture on the website. I was just curious if they're like significantly different. I noticed the font is
actually they're the same. I probably added just few new slides, but I will upload them soon.
Okay.
But essentially the same. May I ask something? So I would like actually some of you to turn on your camera on a volunteer basis. Otherwise, I need to call names, right? Yeah, we need more, probably.
I'm on my desktop and I don't have a webcam for that.
Yeah, that's fine. Like only those who can.
Okay, thanks.
Yeah. Okay, that's good, because the key reason I'm asking this, because for me, I would like to see your look, right? And this is kind of feedback loop. I can basically see whether you understood things right or not, or you're confused, and adjust the way I can explain things. So this helped me to adjust basically the way how I teach. This is what we used to get in normal classes, right? But with Zoom, with the virtual class, is difficult. So that's why I would prefer actually to see you. So Not forcing to all of you, but for those who can, I would appreciate it if you turn on your camera also in the future as well.
Thank you.
Okay, right, so convolutional networks. So basically, and basically you can find more detail in this deep learning book. Actually, this is yeah, I have the physical book here. Let me show you. You probably know that. So this is the book, right? This is the famous book, deep learning book. You don't need to buy it, obviously, but with this link you can find the PDF, right? If you are, for those who are interested to know more about convolutional neural network, also the other type of neural architecture. It is actually a very nice book. I definitely recommend for those who are interested in deep learning. This is a solid, deep, this is one of the basically books that I enjoyed reading a lot, and I learned a lot. This is not a shallow book. This is one of those theoretical and solid books for those who are interested doing research, understand more about machine learning, more specifically about neural networks. Definitely recommend it, right? But to be clear, you don't need to read it for this course fully. And the content of what we discussed today is based on this book. Yes.
I was getting my camera. What book is it that you're discussing, that you're referencing? What's the title of the book?
Deep learning.
Cool. Thank you very much.
Yeah, and the link is, you can find the link to this book basically on the slides. Okay, actually convolutional networks are based on two key concepts. Nothing more than that, just two key concepts. And these two key concepts enable them to scale up, to process basically large input data, right? And by input data, let's not only think about images. Obviously, images are important because we can capture them by camera, but also this involves voice and videos, right? The same thing applies here. So whatever we discuss today and about in general neural networks, even though we may provide example only for images, right? And also for your project to clarify Athena as a framework that you're working with, you're basically doing the evaluation mainly on images, right? But by no means this is restricted to images. You can apply the same stuff if you are interested to basically see how it works on other type of inputs like voice, but definitely you need to figure out different types of transformations for the ensemble defense, right? Obviously, the kind of transformation that we have developed for this current version of Athena that we realized, right? And again, I would like to emphasize it is a framework, right? And we realized several versions of this framework as a defense. So every realization you can think of as a particular defense, right? So for example, when you put together 10 weak defenses, you create a particular instance of this basically adversarial defense. This is one realization of framework as a whole. You can do like 20, you can do 30, or whatever number you want. You can also develop your own transformation for image and add it, right? You can develop transformation for voices, right, and try it, see how it works, whether, for example, this could be interesting scenario that show that, okay, it is easy to trick maybe something like Siri or Alexa, but with this difference, it is not, right? So it blocks this kind of adversarial attacks on voices, and there are papers and research in this direction, basically adding some hidden noise, hidden attacks to voice, which is not, which we cannot detect it by our ear. Like these are hidden commands in the voice that you can add and trick something like Siri or Alexa to, for example, to do crazy thing, right? Purchase something on behalf of you, right? People have shown it. So this becomes very interesting. Here is basically mainly we discuss about images, but basically you can do apply convolutional neural network on any structured data. It is important to be structured, to be grid-like, right? So the structure we are talking about is a grid kind of a structure, like images. Okay, that has so each by structure meaning that each pixel in the image has a special position, also with respect to the other pixels in the image. And you know that for images, you have a grid of pixel values. You might have, for example, 3 different channels, right? For each image. For example, for red, blue, green, each you have 3 channels. Typically, this is for colored images. For black and white, you have 1 channel, right? But it is important to understand this type of architectures. Neural networks apply for a structured data, okay? And one example of maybe non-structured data, if you want to compare, is, for example, you can think about a time series, right? So you have a time series of data, for example, about temperature, about weather. This is a kind of, you can think about this different kind of a structure, is not grid-like a structure, okay? It's a vector-like a structure, if you want to compare it.
Professor, I have a question. Will we get into time series data or ways to
is there any question? I cannot hear it, if there is. Is somebody asking question?
Yeah, Jacob is, but it was pretty quiet.
Yeah. You want to ask?
He posted in the chat saying his mic was bad.
Oh,
he was
sorry,
asking
I cannot see the chat. I'm
Yeah,
so sorry.
I'm reading it out. He was
Okay.
saying that he was asking if we will get into time series data at all.
We might discuss about time series actually, if there is interest, but depends like on the time, because these are more traditional kind of data. It's kind of old way of machine learning, right? But we might discuss about it. Actually, some of you are working on time series data, and like this kind of data also important. We might talk about it a little bit, yeah. Yes, so basically grid-like a structure, and since there are lots of data in video, in images, needs to be processed, right? It's not one number, is a a lot of data in even this one image, right? That needs to be fed into this architecture. And these two ideas, a sparse connection and parameter sharing, enable that to do it very efficiently. Okay, these two simple ideas that basically we plan to discuss about these two very simple ideas to understand what they mean, right? A sparse, what we mean by sparse connection and what we mean by parameter sharing. But at the abstract level, sparse connection means that in contrast to the fully connected kind of deep neural network, as we discussed, you remember that each input is connected to all other units in the network, right? So you remember that we had input here and we had output. So every unit, and by unit we mean one of these neurons probably, is connected to all other neurons in the next layer. The same for this, the same for the other one. But a sparse connection basically means that we want to change this to a kind of a sparser kind of a structure that makes things a lot more efficient. So most units are not actually connected to many other units in here. Okay. And parameter sharing, meaning that for example, in contrast to here, what by parameter, you already know what we mean, these weights. Here we had weight 1, weight 2, and all of these connections were associated to different weights, different like number, right? And we discussed extensively about learning these parameters. But the problem is that, you know, this is optimization. Running optimization is expensive. And optimization, we wanted to learn these weights. So having a lot of weights basically is expensive task, but we want to maybe save, have fewer weights, so have less specific connections. This provides us not only efficiency, but also if we want to learn them, we learn them with higher confidence, right? So because if we have few things to learn with the same data, obviously we get more confidence. This is basically from a statistic. You know about this. So this at a high level, but we will make these things a lot more concrete today with a little bit of mathematics to understand what are these, right? But you got the idea about the sparse connections and parameter sharing. And the other important thing about convolutional neural network, and this is also very, very important, right? It generalizes very well. And especially, it has some property like it preserves some invariances, right? So, for example, if you have a cat, right? If the cat is here in the image, right? If you learn that this is a cat, if you move it here, right? The other side of the input, right? The whole thing is the input, right? You want to still recognize this as a cat, okay? Without learning this as a new data, probably, right? Because it's the same, it's just moved. So with these convolutional neural network have this property that they generalizes very well across with these invariances, right? Like translation, maybe rotation, due to a particular operations that they use, they have this property of good generalization. And basically, this idea is applicable to higher dimension as well, not only 2-dimension, but higher dimensional structure as well. Any question until here? So the idea we want to introduce here is basically convolution as a new operator that we want to learn what it is. And basically, you can think about it as a replacement for matrix multiplication, because matrix multiplication was the key operation we needed to have for densely connected neural network, as you know. Okay. So you can think about convolution as a replacement for matrix multiplication, but as long as we introduce this new operation, everything else would remain the same. So no changes the way how we train the network, right? So we only introduce this new operation and we'll get the property to do, for example, if we used to do training with maximum likelihood, you can do that, right? If you used to do training with backprop, you can still do the same stuff, right? So the exact same thing that we used to do with fully connected neural network, still you can do it with convolutional neural network, right? So we only change the architecture here, the kind of operators that we need to do the calculations, but in terms of processes for optimizing the architecture, everything else would remain the same. And that's nice, right? Because we don't want to introduce a lot of new changes to the way we used to do. And let's talk a little bit, you know about matrix or dot product. Very simple. If you have two matrices, right, A and B, okay, A, for example, and B, in order to calculate C, you basically, for a specific, for example, cell here, you retrieve one specific row, row I, and a specific column, and then you multiply them easily here, right? So AIK, you know that. This is one of these, multiplying by this, and then this by that in order to calculate this set, right? This is Cij within this output matrix that you want to calculate. And you know that this linear algebra, these should match, right? So this is already, I presume you know. And you should, if you have questions, let me know if you want me to explain more, but these are easy. And also we need to know about matrix transpose, right? So you know this operation, you have this A and then you transpose it to get new A, right? So these are basic matrix calculus, right? And you can do transpose to matrix multiplication as well. So you know about this rule, right? In order to get the transpose of this, you can do transpose multiply by transpose A. So these are easy. Well, what is convolution? Convolution is, again, very simple. But think about that you have your input. So this is your input. Think about this as as an image, okay? And image, you have different pixel values. So each of these basically is a 1 pixel, okay? And you have a kernel. Kernel, you can think about this as the parameters that you want to learn or you have learned through a stochastic gradient descent, right? So these kernel have also a grid structure, right? Has also W, X, Y, and Z. So you represent each value by like a variable. And here you have A, B, C, D, whatever. So convolution is really doing very simple operation, right? Imagine that you have this window, you have this kernel, and you slide it through this input structure, right? So you have kernel. Kernel typically is a small grid structure. Your input is basically a large structure. That's the difference in contrast to kernel, right? So input typically is large structure, kernel is smaller, and then you need to slide the kernel over the input to produce the output. So this is the output structure, and again, the output is also a structure, right? Like a grid, the same way. Okay. So you slide the kernel over the input to produce the output, and the rest, the mathematics, is very simple. So, for example, if you put this kernel into this part, right? So you start from upper left, and then you do the product of between corresponding pixels, right? Corresponding cells. A multiplied by W, B multiplied by X, plus E multiplied by Y, and F multiplied by Z. Very simple. And sum them together to produce one cell in your output. You slide it here, okay, doing the same. B, W, C, X, F, Y, and G, Z. Okay, you slide it again. Here, you get C, W, D, X, G, Y, and H, Z. And the same here on the second row as well, right? So imagine as a window kernel, again, a small input is large, you slide it to produce the structure of the output you want to have. Okay, and this output typically are called either in the terminology you might have heard is typically called feature maps, right? So these are called feature maps. So basically each output you can think of as a feature that you have learned, okay? And if you want to get different features, then you might want to have multiple outputs, right? So each of these outputs, you can think about a specific feature that you want to learn, right? Also, these also called channels as well. So if you have heard about channels or feature map, the same thing. Okay. Any question about this? Is it clear? Because these are important. I would like you to understand them very well. Then later on, you learn other more complicated stuff a lot easier. And again, as I said, the input. So, for example, this might in the if it is an image, right? For example, it is an image. You may want to think, okay, it has 3 channels, right? For red, blue, green, right? Sorry, red, green, blue, and if you want to, and this was a one output or one feature map. If you want to have, like, let's say 2 outputs, right? So you need to have a second kernel to produce the second output for you in the same way, right? If you want to have like 3 feature maps, you have then the third kernel, right? So basically, typically, like for example, you can think that in the first layer, input is 3 channels, and then you do this, like you make it like 34, 32, for example, feature maps, and then 64, and so on. You increase these feature maps, and then at the end you reduce it to produce the output. This is the kind of a structure that is more common. Things get big and then get small, typically in convolutional network.
I have a small question.
Yeah, but
so would different attacks or different for different attacks or different weak defenses, would that yield multiple different kernels? If I understand kernel correctly?
No, you're talking about weak defenses, right?
Yes.
You said weak. So each weak defense in Athena is correspondent to one convolutional network, right? So basically, more concretely, in the context of Athena, we discussed about it, right? You have input, right? This was the way you can train, or these currently weak defenses are trained. You have one input. You apply a transformation to the input, right? And this transposed input, right? So you have X, you get T of X, and these X's belong a large set of training example, okay? And then you produce this T of X's, and then you train your network using these T of X's, right? So you get a trained network on the transform input. Basically, think about this as each network is expert for recognizing like flipped images, something like that. But basically, think about each weak defense as a different network that has been trained independently. Make sense?
Yes, thank you.
Sure. So again, this is important to understand because it might be confusing for some of you. So typically you have multiple outputs stacked on top of each other, and for each of these output, you need one kernel to produce that output with this convolution operator. Okay, so that was basically the key operator, and this is the main concept you needed to know about this convolution. And as I said, it's you can correspond it with matrix multiplication. So take an input, produce an output, typically hidden layer, right? You have the input, you have several hidden layers, and you go on until the end. You have two other operators. Deconvolution basically is a multiplication by transpose of a matrix, and you need deconvolution. Basically, deconvolution is similar to convolution, but going from output to the input, right? You remember we started from basically we started from input in the network. We propagate things to produce the output, and you remember for backprop, we needed to propagate the error back to the input, and by error specifically gradient of the loss with respect to the weights, and we discussed about this to propagate things output to the input. And for this, you need the convolution operator to do similar concepts, but for doing things backward, right? But it's very similar concept. And weight gradient computation is useful for parameter sharing, right? And used for backpropagate the error from the output to the weights. So yeah, that's so again to make things probably concrete. If you forgot, let me maybe discuss that here. You see my screen, right? So you can think about this as again, you have input, okay, and then you have your weights, the matrix, right? W, and here I represent it as like a matrix, not one weight, right? To produce some hidden layer, right? And then you have maybe some more hidden layer and so on. And then you produce your loss, okay? You propagate it, you start from input, multiplied by matrix of the weights, right? So here, for example, you can have weight 1, weight 2, weight n, okay, to get to your loss. So basically, this is specifically H1. Again, a matrix is calculated by multiplying the weight matrix to the input, and then again H2 again is a matrix. You got W2 multiplied by H1. Okay, and this is, to be clear, this is not dot product. This is multiplication of matrices, because now we'll put everything into matrices. Previously, you had the small w, right? And this w were basically a vector, right? Now here with this notation, we put together all of this weight vector into a matrix. Okay, that's somehow mathematically we change this, and then you used to produce these elements of these HI, right? for example, H1, like one of these elements, right? I used to produce this by multiplying these weights as a vector to a specific row in this, right? And summing over to produce one of the elements in this matrix. But now with this notation, we change this to a matrix, and then you do the same matrix multiplication all the way down to get this loss, right? And then basically doing the same. So this was your forward pass. And doing the same, you can do backward, okay? You can do the same backward with the loss that you produce, right? You can, for example, here, you get the error on here, right? Then you can propagate back, and this error are this, like, imagine this matrix, this E is, each element is the partial derivative of the loss with respect to weight, right? So you multiply this to basically these weights for this layer, right? Transpose in order to basically going the other way around, right? So you multiply this in order to produce basically the another error, maybe error 1, and then doing the same for error 2 all the way down to have the error with respect to the parameters that you want, right? Basically, this is the way how it works in neural network. So doing one forward pass and then doing one backward pass. This is the way how we used to do, but now you can think about replacing these matrix multiplication with convolution, right? So the math is really the same, but we replace things with a new operator, which is called convolution. But really the same, everything would stay really the same way as we used to do. Any question?
Yeah, so that error 1, for instance, does that correspond to then the first, or, oh, right, okay, never mind, you do have it written there, just to the nth weight. Okay, that actually answers my question.
Yeah, you do the same until you really doing the same kind of operation until you get like the error that you want to get at this for the input, right? And then you use that to adjust your weight. This is what you want to get to adjust your weight accordingly. This is the mathematical description of this, but he also described this with different perspective, from like more granular inner product, also from the computation graph perspective, how things will be done even with framework like TensorFlow. All of these operations basically automatically by the framework. basically think about this TensorFlow as a library that do all of these matrix multiplication for you automatically for calculating the gradient stuff. Any question about this? Okay, let's talk about this. A sparse connectivity is very simple, right? So here in dense in deep neural network or densely connected network, you remember fully connected network, we had each of these input is connected to all units in the output, right? It means that, for example, it really depends how you want to interpret things, right? So, for example, this little guy, this X3, affect S1, S2, S3, S4, S5, right? Why? Because you calculated S5, for example, by doing what? By doing weight 1 with X1 plus weight 2 with X2 plus weight 5 with X5. All of this, right? Including X3 with weight 3, right? So plus, sorry. So this, you see this term? So this appeared here for calculating S5. Similar for S4 for calculating S3, the same, right? So this little guy affect the value that you get for all of these units in the next layer. Okay, so this is what's happening really in dense connections, right? In deep neural network, which have dense connection between each layer, and this is what you have learned, right? We discussed, right, about the architecture of neural network. So the neural network stuff that we discussed was has these dense connections, if you remember. But with a sparse connection, this is slightly different, and this is important to think about it, right? Is that this little guy affecting X2, X3, X4, but not S5 and S1. Okay, so it has a local connection to a limited number of units in the next layer. And this number really depends on what? Can you guess what this number depends?
You mean like the selection of the number of connections from an input to an output?
Yeah. So why instead of 3 is not 4?
It depends on the kernel size.
Yeah, fantastic, right? So you remember here, back to here. The kernel size is 2, right? So see here, you see A, right? Or maybe think about CB, okay? And where else it appears? Appears also here, okay? But not here. So it appears into units, right? So, but if we had a larger kernels or smaller kernel, that would be different, right? So, so basically, each input with this property of that we have with kernel and convolution operator really make the network sparse. So each input is connected to only a handful of output units, not all of them previously we had with densely connected network. Why it is important? Why do you think it might be important to have this?
Well, I know for one reason, computationally speaking, it's just more intensive to compute for all of the nodes.
Yeah.
And I suppose another reason is that whatever operation it is that we're trying to encode through these convolutions or through these connections, they might not necessarily require a connection to all of the next nodes. So if we add like all of those extra connections, if we have more than we need, I suppose, then we might have some issues of, I guess, overfitting. Yeah.
Right. So basically, first of all, you have much less stuff to store, right? And much less stuff to compute. So basically, nice cat. So basically, you have less stuff to store, so it becomes much more efficient in this way, right? So these are the properties that you get with this sparse connection, as we discussed. And these numbers really depends on the size of the kernel. You can also think that the other way around, right? So this was one view, right, from the input to the output. Now you can think about the output, like this S3, if you can think, only depends on limited number of input units, right? So S3 only depends on X2, X3, X4, but previously this was basically dependent on all of the input units. So all of these X1, X2, X3, X4, and X5 basically affect the value of S3 due to this, right? For calculating S5, we needed to have value of all of these X's. So the same thing, but two different perspectives that you can look at it. And these basically sparse connectivity provides some of these properties that will make things concrete about the invariances that you get with this type of neural network. But like the key takeaway is that you have much less stuff to store because of this sparse connection, and you see that this is really sparse, right? Comparing to these crazy connections. But like one question could be, okay, maybe you say that, okay, what would happen to learning, right? So maybe these stuff do not learn about the whole. So basically, this stuff do not cover the whole input space, right? And basically, that might be true. But if you think about multiple layers, right? That might be true here for when we have only two layers, right? We have input and like the next layer or output, right? So input, output, no hidden layer. That might be true, that like this guy may not ever learn about these two guys, but if you think about deep architectures, right? This is a concept called receptive field. So if you think about G3, and yes, G3 only depends on H2, H3, H4, but H2 basically sees H1, sees X2, and sees X3. The same for H3, X2, X3, X4, and H4 sees H3, X4, and X5, right? So now as a result of this hierarchy, basically the whole input data was reached to this output G, right? So if you add these hidden layers, and that's why we need hidden layers to grow the receptive fields and see the whole picture, right? This is why we need hidden layers and why these stuff going deeper and deeper, right? Basically learning more about the features in the input from different angles, right? And these different angles are really produced by these features or kernels, basically, that we have. And yeah, that was basically about the sparse connectivity, right? The other concept is about parameter sharing, right? And that's also important. So what happened here is that in traditional densely connected network, basically every parameter was different, right? So we had a large parameter, right? So each of these connections, right? Again, we had W1, W2, W3, whatever, right? So each of them was a different parameters, right? That we need to learn differently, okay? And each of these stuff was really a separate thing, separate entity. But in convolution, convolution actually share the same parameters across the spatial connections. So basically this guy is the same as this guy, same as this guy, same as this guy, and same as this guy, okay? This is a specific connection. Do you know the reason why this happens?
Could you recircle the nodes you're referring to? Everything being in purple is a little bit confusing to keep up with.
Sorry, say it again.
You were showing which nodes you were focusing on. Could you
yes, so I'm
those in
saying
red
that this guy, this guy, this guy, this guy, and this guy are basically the same, right? So if you call this W1, this is also W1, this is W1, this is W1, W1, right? But here, like we had like only W1 here, and the rest was W2, W3, whatever. They were separate. No parameter sharing. Here we have like the same parameter, but in different places. Do you know why this has, how we got this property?
Because it uses the same kernel.
Exactly, right? So you remember here we had the same kernel, we just slide it over the input, right? But it's the same kernel. So we have the same kernel sliding over the input, but really the kernel has is the small sizes and just slide it. So sharing means that like this thing slide over this input, and that's how sharing happens. Like it's two different viewpoints that you can think about this, right? This is like a kind of 2D structure, but here is from different perspective, right? So basically making these things, imagine that now you see these things as a non-structured, right, input, but if you put this into a structure, you slide the kernel, then this parameter sharing happens. Any question?
So do we have then one kernel per like layer? Otherwise, like, you know, we would just have like the same, I feel like we'd have the same weights being repeated through each successive layer. It might not be, or it might be, I feel like that would be like a really restrictive system, I guess.
Yes, so for each, so this stuff, this kernel, right, again, I said like when you have one input, right, this kernel slide it over, give you one output, give you one feature map, right? So if you want two feature maps, you need another kernel, right? If you need 3 feature maps for like for this layer, right? For this, for the third output, you need the third kernel. Okay, and you learn them separately, right? You learn these parameters inside your kernel, right? This W, X, Y, Z. These stuff. So imagine that like this guy is for detecting edges, right? And this guy is for detecting some other features, right? Detecting circles, for example, right? So each of them is for different, could be associated or thought about as different features that you want to learn, right? Or basically there are, so in better way is that these different kernels enable you to learn different features, right? Because the features are really in your output, right? So this kernel help you to learn these specific features like edges. This kernel help you to get this output, the other output for circles, for example. Okay, and as you move down to these hidden layers, these features becomes more high level, right? It generalizes better and due to this, right? So if you move deeper, right, you learn higher level features, right? Here, maybe you want to learn like edges, circles, the stuff, low level features, and then you move down to the architecture. You learn better about or higher level features of your input. Right, and this parameter sharing really again help you to right. So you have one parameter here shared across these different inputs. So it helps you to store less parameters, right? To save things, save basically memory, computation, and also you need to learn this once, right? Previously, you need to learn these like different weights, right? So this was different from this guy, was different from this guy, was different from this guy, different from this guy. Like not only you need to have memory to store them, but also for learning them, you need data, and like you get right? Less generalization if you use the same size, right? So the same data for less parameters, obviously you get better confidence over your learning, right? When you do this stochastic gradient descent. Right, so for example, think about this kernel, and this is your input, and this kernel, imagine that like -1, right, for detecting edges, where the edges are, okay? So you slide it over the input, you get something like this as an output, and this gives you where the edges of these images are, right? Like here, right? So this is the way how you can think about it. This is one of your feature maps, right? The output that you produce.
Would the orientation of this kernel here like make it more sensitive to edges in a vertical, from like a vertical difference as opposed to a horizontal difference, like across the picture?
Say it again.
So would this kernel, I guess, being a 2 by or a 1 by 2, would that make it more sensitive in some way to edge differences in edges? If you imagine like there's an edge that's horizontal versus an edge that's vertical, would it be more sensitive to like one than the other?
Yeah, maybe, yes. As you can see, maybe this is detecting these horizontal edges better, right? Yeah, maybe. That's why you have different kernels, right? Right. And yeah, think about like efficiency of convolution is that, like, imagine an input size of this 320 by 280, and you have a kernel size 2 by 1, right? And this is your output size, right? You can imagine why you have 1 here, right? Because of this kernel size 2. So here for convolution, how many storage you need? How many things you need to store? 2, right? It's 2 by 1, right? You need to learn these weights, right? You have 2 weights. You have W1, W2. You need 2, but for the other densely connected, you need this many, right? And why this many? Why do you think? Why is that the case?
That's the array corresponding to, or not the array, sorry, that's the matrix corresponding to the features of each input. So 319 times 280 is the matrix associated with all the features. And then the 3 at the end, that is the number of nodes for each layer.
Yeah. Or maybe you guys think about it and we'll discuss next time, right? Maybe some of you could explain why we need these many, and what is the difference that you get with respect to densely connected network, right? And why you need that many parameters to store, right? Okay, let's stop here, but think about this, because this stuff would be when we connect to the hardware are important. But basically, the key takeaway that you had for today is that you now know about convolution, you know why they are important, and some basic concepts. And we will continue afterward with more details. Okay, have a good day. See you soon.
Thank you very much. Have a good
Thank
afternoon.
you.
Bye, Professor.
Sure.
Bye.